Yes, there is a requirement in the National Electrical Code, specifically Article 110.3b, that addresses the use of circuit breakers from the same manufacturer in a given electrical panel. It states that circuit breakers of the same manufacturer shall be employed in any given branch circuit or feeder. This requirement is primarily in place for two main reasons: safety and reliability. Firstly, safety is paramount. Using circuit breakers from different manufacturers within the same panel can introduce compatibility issues. These incompatibilities can lead to several electrical hazards, including overloads, short circuits, and potentially fires. Different manufacturers may design their circuit breakers with varying physical dimensions, contact configurations, and interrupting capacities. Mixing different brands can compromise the proper seating and connection of the breakers within the panel busbars. This can lead to loose connections, arcing, and overheating, all of which significantly increase the risk of electrical fires. Furthermore, circuit breakers from different manufacturers may have different tripping characteristics, even if they are rated for the same amperage. A mismatch in tripping characteristics can lead to one breaker failing to trip when it should, potentially overloading other circuits or equipment and creating a dangerous situation. Secondly, reliability is a key factor. Circuit breakers from different manufacturers may exhibit varying performance levels and tripping characteristics under different fault conditions. These variations can affect the overall reliability and protection provided by the electrical system. All circuit breakers are designed to trip within a specific time frame when an overload or short circuit occurs. However, the exact tripping curve, which defines the relationship between the overcurrent and the tripping time, may differ significantly between manufacturers. If breakers with different tripping curves are used in the same panel, it can be difficult to coordinate the protection system effectively. For example, a downstream breaker may not trip quickly enough to clear a fault before an upstream breaker trips, causing unnecessary outages and potentially damaging equipment. The requirement for using circuit breakers from the same manufacturer applies to the main breaker box, which is also known as the service entrance panel, and any subpanels that are fed from the main panel. This ensures that the main distribution point of the electrical system and its immediate extensions maintain consistent protection characteristics. However, the requirement does not necessarily apply to individual circuits within a branch circuit or feeder. In these cases, different types of circuit breakers can be used, as long as they meet the specific electrical requirements for the circuit and are appropriately rated for the application. For example, an electrician can use a ground fault circuit interrupter, often called a GFCI, breaker from a different manufacturer in a branch circuit, as long as it is properly rated and compatible with the panel. However, the NEC does provide comprehensive guidelines for selecting and installing circuit breakers, and it's important to adhere to those guidelines to ensure the safety and reliability of the electrical system. Before installing or replacing any circuit breakers, it's always recommended to consult with a qualified electrician to ensure compliance with all applicable codes and regulations. Firstly, understanding the types of circuit breakers is important. Common types include standard thermal-magnetic breakers, ground fault circuit interrupters, arc fault circuit interrupters called off-size and high interrupting capacity breakers. Secondly, circuit breaker ratings must match the circuit requirements. This includes voltage, amperage, and interrupting capacity. Thirdly, always follow the manufacturer's instructions for installation and maintenance. Incorrect installation can compromise the breaker's performance and safety. Fourthly, regularly inspect circuit breakers for signs of damage or wear. Replace any breakers that are damaged or not functioning properly. Fifthly, use appropriately sized conductors for the circuit. Undersized conductors can overheat and cause a fire hazard. Sixthly, ensure that all connections are tight and secure. Loose connections can cause arcing and overheating. Seventhly, properly label all circuit breakers for easy identification. This helps in troubleshooting and maintenance. Eighthly, consider using surge protection devices to protect sensitive electronic equipment. Surges can damage or destroy electronic devices. Ninthly, ground fault circuit interrupters are required in areas where there is a risk of electric shock, such as bathrooms and kitchens. Finally, arc fault circuit interrupters are designed to protect against arc faults, which can cause fires. If a homeowner or business owner are unfamiliar with these aspects, consultation with a qualified electrician would be beneficial for their safety and their equipment. Ignoring the NEC requirements and manufacturer recommendations can lead to serious consequences, including electrical fires, equipment damage, and personal injury. The NEC requirements are in place to protect people and property from electrical hazards. Compliance with the NEC is not just a matter of following the law, it's also a matter of safety. It's also good to note that local jurisdictions may have additional requirements or interpretations of the NEC, so it's always best to check with the local building department or a qualified electrician to ensure full compliance. The NEC is updated every 3 years, so it's important to stay current with the latest edition. Changes to the NEC can affect the requirements for circuit breakers and other electrical equipment. In addition, proper maintenance of electrical panels is crucial for ensuring safety and reliability. Regularly inspecting the panel for signs of corrosion, loose connections, or other damage can help prevent problems before they occur. Circuit breakers should be tested periodically to ensure that they are functioning properly. This can be done by a qualified electrician using specialized testing equipment. Furthermore, it is a safety best practice to never overload circuits. Overloading circuits can cause circuit breakers to trip frequently, which can damage the breakers and the wiring. It can also create a fire hazard. The total load on a circuit should never exceed the circuit breaker's rating. In the realm of electrical safety, it's also important to understand the concept of selective coordination. Selective coordination refers to the practice of designing an electrical system so that the circuit breaker closest to fault trips first, minimizing the impact on the rest of the system. This is achieved by carefully selecting circuit breakers with appropriate time current characteristics. By understanding and implementing selective coordination, you can improve the reliability and safety of the electrical system. Electrical distribution systems are designed to deliver electrical power safely and reliably from the utility source to various loads within a building. The design of an electrical distribution system involves careful consideration of several factors, including the size and type of loads, the voltage and current requirements, and the applicable codes and standards. One of the key components of an electrical distribution system is the overcurrent protection devices, which are designed to protect the system from overloads and short circuits. Overcurrent protection devices include circuit breakers, fuses, and other devices that interrupt the flow of current when it exceeds a predetermined level. Circuit breakers are commonly used in electrical distribution systems because they can be reset after they trip, unlike fuses, which must be replaced. The selection of circuit breakers for an electrical distribution system is based on several factors, including the voltage, current, and interrupting capacity requirements. The interrupting capacity of a circuit breaker is the maximum amount of fault current that the breaker can safely interrupt. It's important to select circuit breakers with an interrupting capacity that is sufficient for the potential fault current at the installation location. In addition to the NEC, other standards and guidelines provide recommendations for the design and installation of electrical distribution systems. These include standards from organizations such as the Institute of Electrical and Electronics Engineers, often called the IEE, and the National Electrical Manufacturers Association, or NEMA. In conclusion, adhering to the NEC requirement for using circuit breakers from the same manufacturer in main breaker boxes and subpanels is crucial for ensuring electrical safety and reliability. It helps prevent compatibility issues, maintain consistent protection characteristics, and minimize the risk of electrical hazards. Consultation with a qualified electrician is always recommended to ensure compliance with all applicable codes and regulations and to select the appropriate circuit breakers for the specific application. In the world of electrical engineering, the selection and application of circuit breakers are governed by a complex interplay of standards, regulations, and best practices. Electrical engineers must have a thorough understanding of these factors to ensure the safety and reliability of electrical systems. In addition to the NEC and other standards, electrical engineers also rely on their own experience and judgment when selecting and applying circuit breakers. They must consider the specific characteristics of the electrical system, the types of loads being served, and the potential hazards that may be present. Furthermore, the coordination of circuit breakers within an electrical system is a critical aspect of electrical system design. Coordination refers to the process of selecting and setting circuit breakers so that they operate in a coordinated manner, minimizing the impact of faults on the system. The goal of coordination is to ensure that only the circuit breaker closest to the fault trips, while all other circuit breakers remain closed. This minimizes the outage area and allows the rest of the system to continue operating normally. The process of coordinating circuit breakers involves analyzing the time current characteristics of the breakers and selecting settings that provide the desired level of coordination. This requires careful consideration of the fault current levels, the breaker interrupting capacities, and the system voltage. In addition to overcurrent protection, electrical distribution systems must also provide protection against other types of faults, such as ground faults. Ground faults occur when a live conductor comes into contact with a grounded surface, such as a metal enclosure. Ground faults can cause severe electric shock hazards and can also damage equipment. To protect against ground faults, electrical distribution systems are equipped with ground fault protection devices. Ground fault protection devices are designed to detect ground faults and quickly interrupt the flow of current, preventing electric shock and equipment damage. Ground fault protection is required by the NEC in many applications, particularly in areas where there is a high risk of electric shock, such as bathrooms, kitchens, and outdoor locations. The design and installation of electrical distribution systems require a high level of expertise and attention to detail. Electrical engineers must have a thorough understanding of the applicable codes and standards, as well as the characteristics of the electrical equipment being used. In addition, they must be able to analyze the system performance under various fault conditions and select the appropriate protection devices. The safe and reliable operation of electrical distribution systems depends on the knowledge and skill of the electrical engineers who design and install them. These engineers ensure they are staying current with the latest technologies and best practices in the field. The evolution of circuit breaker technology continues to improve the safety and reliability of electrical systems. Innovations such as arc fault circuit interrupters and electronic trip units provide enhanced protection against a wider range of electrical faults. As technology advances, electrical engineers must stay abreast of these developments and incorporate them into their designs to ensure the highest levels of safety and performance. Electronic trip units offer a range of advanced features, such as adjustable time current characteristics, ground fault protection, and data logging capabilities. These features allow electrical engineers to fine-tune the protection of the system and monitor its performance over time. Moreover, surge protection devices are an important component of electrical distribution systems, particularly in areas that are prone to lightning strikes or other voltage surges. Surge protection devices are designed to protect sensitive electronic equipment from damage caused by voltage surges. They work by diverting the surge current to ground, preventing it from reaching the protected equipment. Surge protection devices are available in a variety of configurations, including whole-house surge protectors and point-of-view surge protectors. Whole-house surge protectors are installed at the service entrance of a building and provide protection for all of the electrical equipment connected to the system. Point-of-view surge protectors are plugged into individual outlets and protect the equipment plugged into that outlet. Another key aspect of electrical system design is the selection of appropriate wiring methods. Wiring methods refer to the types of conductors, raceways, and other materials used to install electrical wiring. The NEC specifies the allowable wiring methods for various applications based on factors such as the voltage, current, and environmental conditions. It's important to select wiring methods that are appropriate for the specific application to ensure the safety and reliability of the electrical system. In addition to the NEC, other standards and guidelines provide recommendations for the selection and installation of wiring methods. These include standards from organizations such as the Insulated Cable Engineers Association, often called ICER, and the National Electrical Manufacturers Association. The proper grounding of electrical systems is essential for safety. Grounding provides a low impedance path for fault current to flow back to the source, allowing the overcurrent protection devices to trip quickly and clear the fault. Grounding also helps to reduce the risk of electric shock by providing a safe path for current to flow in the event of a ground fault. The NEC specifies the requirements for grounding electrical systems, including the size and type of grounding conductors, the methods for connecting to ground, and the testing requirements. Proper grounding is a critical aspect of electrical system design and installation. Electrical safety is a shared responsibility. Electrical engineers, electricians, and homeowners all have a role to play in ensuring the safe operation of electrical systems. Electrical engineers must design systems that comply with all applicable codes and standards. Electricians must install and maintain the systems in accordance with the manufacturer's instructions and best practices. Homeowners must use electrical equipment safely and report any electrical problems to a qualified electrician. By working together, we can create a safe electrical environment for everyone.